Ever wondered how particles can be in two places at once or teleport across vast distances? Welcome to the perplexing world of quantum phenomena, a realm where the rules of classical physics are cheerfully tossed out the window. Here, subatomic particles like electrons and photons can exist in a state of superposition, being in multiple states simultaneously. Imagine being both at home and at work at the same time. That's superposition for you. Quantum teleportation, on the other hand, is no less mind-boggling. It's not about vanishing and reappearing Star Trek style, but rather, it's the instantaneous transfer of information from one particle to another, regardless of the distance separating them. To help us navigate this quantum conundrum, there's the McGinty Equation. This equation, a beacon in the quantum fog, provides insights into the behavior of these subatomic particles, taking us one step closer to understanding the fundamental building blocks of the universe. So, brace yourself and prepare to dive deeper into the quantum realm with the McGinty Equation. The McGinty Equation, at first glance, may seem daunting. However, fear not, for it is far simpler than it looks. Let's break it down piece by piece. The equation consists of three main components: Pxt, Psqft xt, and Psfractal xtdmqs. Firstly, we have P's xt. This represents the state of a quantum system at a given point in space and time. This is the core of our equation, the heart of the matter, if you will. It's the quantum equivalent of saying what's happening right here, right now. Next up, we have Psqft xt. This is the solution of the free quantum field theory. In layman's terms, this is the answer to the question, what would happen in a perfect quantum world with no other forces at play? It's the base state, the starting point from which we can begin to explore the more complex interactions within the quantum field. Lastly, we have the Psfractal xtdmqs component. This represents the fractal structure of the quantum field. Now, fractals are a bit of a tricky concept, but think of them as patterns that repeat themselves at different scales. Like the spirals in a snail's shell or the branching of a tree, quantum fields also exhibit this self-similar behavior. The fractal component of the McGinty equation introduces this self-similarity into the mix. It takes into account the fractal nature of the quantum field, allowing us to delve deeper into understanding the behavior of subatomic particles. This component can be derived using integral calculus, Laplace transform, and the convolution theorem, allowing us to explore the fractal nature of quantum fields. So, there you have it. The McGinty equation, though seemingly complex, is simply a way of representing the state of a quantum system, taking into account both the ideal behavior of quantum fields and their fractal structure. Each component of the McGinty equation plays a unique role in explaining the behavior of subatomic particles. In the vast cosmos, gravity is a force that no particle can escape. But how does it fit into the quantum world? The answer lies in the modified McGinty equation, a mathematical expression that combines the principles of quantum mechanics and general relativity. Let's unpack this equation a bit. Psxt represents the state of a quantum system at a certain point in space and time. This is split into three components. The Psqft term is the solution of the free quantum field theory, which describes the behavior of quantum particles in the absence of any external influences. The fractal xxtdmqs term represents the fractal potential, a self-similar structure that arises from the inherent unpredictability of quantum systems. But the star of our show today is the gravity Stg term. This term represents the effects of gravity on the quantum field. The g in this term is a parameter that characterizes the strength of the gravitational force. It's our mathematical handle on gravity's role in the quantum world. So what does this mean in layman's terms? It implies that gravity, the force that keeps our feet firmly on the ground, also has a hand to play in the realm of the infinitesimally small. It suggests that gravity, like the quantum world, is not just a simple force, but a complex interaction that can influence the state of quantum systems. The modified McGinty equation is a significant step in our understanding of the universe. By incorporating gravity into the quantum equation, we're beginning to see how the macroscopic world of stars and galaxies is connected to the microscopic world of quantum particles. It's a meeting of the incredibly large and the incredibly small, a convergence of the universal and the particular. And that's the beauty of science. It's a never-ending quest to understand the universe, from the largest galaxies to the smallest particles. The modified McGinty equation helps us bridge the gap between the quantum world and our familiar reality. We have journeyed through the intricacies of the McGinty equation. Now, it's time to see the bigger picture. In the realm of quantum physics, the McGinty equation is a cornerstone, a key that unlocks the door to the enigmatic behavior of subatomic particles. It's a marvel of mathematical and physical insight, combining the free quantum field theory PSQFT XXT, the fractal potential PS fractal XT DMQS, and the gravitational perturbation piece gravity XTG. In essence, the McGinty equation allows us to delve into the heart of quantum phenomena. It permits us to explore quantum superposition, the concept that particles can exist in multiple states at once. This isn't just a fascinating theoretical concept, it's a fundamental principle underpinning the burgeoning field of quantum computing. Quantum computers, unlike their classical counterparts, can process vast amounts of data simultaneously, thanks to superposition. It's the McGinty equation that helps us understand this and make it possible. But the equation's reach extends beyond computing. Take quantum teleportation, for example. This isn't science fiction. It's a real and experimentally confirmed process where the state of a particle can be transmitted instantaneously across distances. It's the McGinty equation that provides a framework for understanding this seemingly impossible phenomenon. And let's not forget the gravitational force, G. This parameter in the modified McGinty equation represents the perturbative effects of gravity on the quantum field. It's a crucial step towards reconciling quantum mechanics and general relativity, two pillars of modern physics that have often been at odds. In essence, the McGinty equation is a map of the quantum landscape, a guide to a world that defies our everyday intuition. It's a testament to human ingenuity and the relentless pursuit of understanding. The McGinty equation, a beacon in the enigmatic world of quantum phenomena, continues to shed light on the fundamental aspects of our universe.